let's tackle the biggest question there is. Where did all of, well, this come from? Some of the wildest theories in physics today suggest that our entire universe could have just popped into existence from absolute nothing. But does quantum mechanics really give us a universe without a cause? Let's dig in. This quote from physicist Paul Davies really hits the nail on the head. The whole argument is that the fundamental weirdness of the quantum world, all its probabilities and uncertainties, might just be the ultimate loophole, a way for a cosmic beginning to happen without a beginner. But, to really see if that idea holds any water, we've got to understand the bizarre rules of the quantum game first. Okay, first up is something called superposition. The easiest way to think about it is like a spinning coin. While it's in the air before it lands, is it heads or tails? In a way, it's kind of both. That's superposition. A quantum particle, before we look at it, isn't in one spot. It's more like a cloud of possibilities, existing in all its potential states at the very same time. And then we've got the famous uncertainty principle. Now, get this. This isn't about our tools not being good enough. It's not a problem we can solve with better technology. Quantum theory says this fuzziness is baked into the fabric of reality itself. The more you know exactly where a particle is, the less you can possibly know about where it's going, and the other way around. And this idea, this built-in uncertainty, it sparked one of the biggest philosophical fights in the history of science. Yeah, this clash basically split the world of physics in two, and it pitted two of the greatest minds ever against each other. The question they were wrestling with was huge. Is reality something that's just out there waiting for us to find it? Or does the act of us looking at it somehow bring it into existence? So, in one corner, you had Niels Bohr and his Copenhagen Interpretation. His side basically said that before you measure something, a question like, where is the particle, is just meaningless. The act of measuring is what forces the universe to pick an answer, effectively creating that little piece of reality. And in the other corner was Albert Einstein, who fought hard for realism. He was convinced that the universe has definite properties whether we're looking or not. Our measurements just reveal what was already there all along. Bohr's view is, it's pretty out there, and this quote just lays it all out. To him, all of the beautiful math of quantum mechanics wasn't describing some secret, hidden reality. Nope. It was just a set of tools that let us predict what we'd see in our experiments. In this picture, the scientist isn't just watching the show. They're literally part of the cast, helping to create the reality they're studying. And here's Einstein's legendary clapback. He just could not get on board with the idea that the universe, at its very foundation, was based on the random roll of a cosmic dice. He felt deep in his bones that there had to be a deeper hidden order to things, and that quantum theory was just incomplete. This wasn't just some friendly debate. It pointed to a giant, gaping hole in the theory. And this huge disagreement brings us right to the core of the whole mess, a puzzle that physicists are still arguing about to this day, and it's called the measurement mystery. It sounds like such a simple question, doesn't it? But here's the crazy part. The standard quantum rulebook is shockingly quiet on this. What actually counts as a measurement? Does it have to be a person, a cat, a machine? Where's the dividing line between a quantum system just bumping into another one and an official measurement taking place? The theory just doesn't give us a straight answer. And it's not some old, forgotten problem. Modern physicists, like the Nobel laureate Roger Penrose, say it as bluntly as possible. He argues this vagueness actually makes the whole theory inconsistent. The problem is all centered on that weird moment of measurement, what they call the collapse of the wavefunction. That's just the fancy term for that cloud of possibilities suddenly snapping into a single concrete reality. Okay, so here's the heart of the problem. As long as nothing's looking, a quantum system just cruises along, evolving smoothly and predictably. You can describe it perfectly with this beautiful piece of math called the Schrödinger equation. But then, the instant a measurement happens, bam, the rulebook gets thrown out the window. That smooth, predictable evolution just stops, and the system suddenly, violently, and randomly jumps to one single state. Why? How does that jump happen? Standard quantum theory just shrugs its shoulders. So this is where some really fascinating alternative ideas start to come into play. What if the issue isn't that reality is random? What if our theory is just incomplete? What if there's a cause for this jump that we've just been missing all along? So here's a really cool idea from our source material. What if that jump, that collapse, isn't random at all? What if it's more like a pre-programmed response, something baked into the very structure of the particle itself? In this picture, a measurement isn't a random event. It's like a specific key being put into a specific lock.
It has a predictable outcome. This table gives us a bit of a peek at how this might work. See, a particle isn't just a blank dot. It has its own internal properties. Some of those, like coherence, which is basically its ability to act like a spread-out wave, are what allow for all that weird quantum superposition stuff. But it also has other properties, like mass and having a definite position, which are classic, solid, particle-like behaviors. The idea here is that a measurement doesn't invent a particle. It just interacts with these existing properties and forces a change. And this is the real game changer. In this view, the observer isn't some magical creator of reality. No, instead, the measuring device just interacts with the particle in a way that disables the properties that allow it to act like a wave. It shuts down the coherence. And once that's gone, all that's left are the particle-like properties. So, reality isn't created from nothing. The other possibilities are just removed, revealing the one outcome that was left. Okay, so, armed with this totally new perspective, one that puts cause and effect back into the picture, let's circle all the way back to our starting point. If quantum events aren't truly random, then what does that do to the whole idea of a universe from quantum nothingness? This is the million-dollar question, right? The entire universe from nothing argument rests on the idea that quantum events are truly, fundamentally uncaused. But if this alternative view is correct, if these events are actually just structured responses to specific triggers, then the whole foundation for a causeless universe starts to look really, really shaky. And the problems don't stop there. First off, the so-called quantum vacuum isn't nothing in the way you and I think of it. It's a buzzing, fizzing sea of energy and virtual particles. Second, for anything to pop out of that vacuum, it has to follow a set of rules, the laws of quantum mechanics, which had to exist beforehand. But where did those laws come from? And finally, that uncertainty principle we talked about, it doesn't actually get rid of cause and effect. It just says we can't see it perfectly. Which leaves us with this final, absolutely massive question. The laws of quantum mechanics are incredibly precise, elegant, and finely tuned. The suggestion that these incredibly complex laws just existed and then governed the leap from a structured nothing to our intricate cosmos, well, that might just be a bigger leap of faith than any other explanation out there. It really makes you wonder, who or what wrote the rulebook for the universe?